As promised, here is a little video that will help you be familiar with the last part of the chapter, which is dealing with the torque on a current loop. So I just wanted to review the last results that we got in the end of class, which was what happens if you have a current in a magnetic field. Well, because the current is actually moving charges, of course it's not surprising that a piece of wire that's carrying a current will feel a force in a magnetic field. One of the interesting things that we saw in the expression for that force is, because of the fact that the current is a scalar quantity, we can't suddenly make it a vector. That doesn't make any sense. So the vector becomes the length of the wire, and then the direction would be given by the direction of the current. And so then the expression for the force on that piece of wire is IL cross B. Let's look at a problem and see if we can sort of see how we would apply that. So here we have a vertical wire carrying current vertically upward in a region where the magnetic field vector points towards the north. What is the direction of the magnetic force on this current due to the field? This is a problem that uses the idea that we've talked about before, where we imagine a plane that's tangent to the Earth, that plane holds the north, south, east, west directions, and then this would be up and this is down. Those are the third dimensions. If we're looking at the piece of paper where we have the north, south, east, and west, in this particular picture, the direction of the magnetic field we could put is like this. Here's my B, because that is pointing north. Our wire carries the current vertically upwards, so the current is going to be coming up at us in that plane that's tangent to the Earth. So that's I. So when I'm doing the force is IL cross B, I'm going to start with my fingers pointing out at me in the direction of the current. I'm going to curl my fingers upward in the direction of the magnetic field, and the direction of the force that I'll get is going to be to the left or in the westward direction. And that's how we would do that. So that was just a little review to see if we understand that. So let us look at the problem of the force and the torque on a current loop. And the first thing we're going to do is we're going to look at two separate examples. The first one, and I like to use a square loop because we have straight pieces then, and it just seems like it's a little bit easier. And we're going to imagine that the current is traveling around in a counterclockwise direction. So that's the direction of the current. So, and let's make the magnetic field, let's make it go into the page. So I'm going to make the X's to represent the magnetic field. And so that's B. So we're going to use this idea that F equals IL cross B, but we have to do that for each side of the loop because of the fact that on each side the current's traveling in a different direction, so our L is going to change. I'm going to start on the right hand side. I'm going to point my fingers up in the direction of the current, curl my fingers into the page, and I'm going to get a force to the left. Now I'm going to move to the top part of the wire, point my fingers to the left because that's the direction of the current, curl my fingers inward in the direction of the magnetic field, and my thumb points down. So that's to the downward direction. Move to the left hand side. I'm going to do my right hand rule again. You should be getting better at this, and you should have seen that that's going to be a force to the right. And finally the bottom, if we do IL cross B, we have a force upward. The forces are all going to cancel out. The forces in the left and the right are equal in magnitude but opposite in direction, and the forces in the top and the bottom are equal in force and opposite in direction. So if we look at the total forces acting on this loop, we get 0. And the way the forces are, it wouldn't cause any sort of rotation, and that's kind of what we're looking for when we look at torque, right? So let's draw a different scenario, because what we're looking at in these scenarios are sort of extremes, if you will, in how much torque you're going to feel. And sort of the extremes are governed by sort of the orientation of the loop of wire and the magnetic field. So the first one is with the magnetic field kind of goes through the area of the loop, and we found that there was no torque. And so in the other one, we're going to say, what if the magnetic field is in the plane of the loop? And so we're going to see what the result is there. So this is what I'm going to do in this case. Keep in mind that this magnetic field could have pointed in a couple different directions, but I just chose one, and that's the one we'll work with. So here the magnetic field is pointing up. And so now I'm going to do my right-hand rule, my F equals I L cross B, and I'll do it on all four sides. I'm going to start on the right-hand side. The current's traveling up and the magnetic field's traveling up, so they're parallel to each other. So on the right-hand side, there's no force. Now when I do the top, if I do the right-hand rule, I'm going to point my fingers to the left, I'm going to curl my fingers up, and when I did that, my thumb had to point into the page, so on the top, I have a force that goes into the page. On the left-hand side of this loop, now the current and the magnetic field are anti-parallel, so there's no force over here. And now I'm going to do finally the bottom, and when I do the I, L cross B, I actually get a force coming out at me. So now, the sum of the forces acting on this loop is 0, but the sum of the torques is not 0, because you can see that what happens is I'm producing an equal and opposite force on each side of this loop, and that's going to actually cause it to rotate, and it's going to rotate in a way that the bottom of the loop is going to be sort of coming out at me, and the top of the loop is going to be going in. And so the axis of rotation is going to be along this line. So we do see that there's definitely a torque there. If we wanted to figure out what that torque was, so if I said, in this case, if this, the length of this, so I just call this L, the magnitude of the force that's exerted on each side is going to be I, L, B, because they're perpendicular to each other. And the torque is going to be, for each force, is going to be L over 2 ILB plus L over 2 ILB. And that's because this is like my radius, and it's going to be half of the length of the loop. Because remember it said my loops were square, so dimensions in the same way our dimensions are equal in each direction. So I got I L squared B, and this is actually L squared is like the area. So this is how we would express the torque, at least the magnitude of it, for this particular situation. It turns out that we actually talk about, remember I saw my expression, the magnitude of the torque for that last one was IAB. We actually sort of use the product of those terms, the current and the area that they enclose. So keep in mind this is the area, at least how big it is, but of course the vector is going to be perpendicular to that. We call this mu, which is the magnetic moment. It's simply a product of the current and the area vector. But what we're going to see eventually is that the torque that is produced by this current carrying loop in a magnetic field can be expressed as mu cross B, or IA cross B. The way that we get the direction of the magnetic moment and the area is we wrap our fingers around the loop in the direction of the current flow, and our thumb will then be pointing in the direction of the magnetic moment and the area. And so hopefully that helps clear up some of the questions that there were about the magnetic moment. Sorry about that. So what I want to do now is I want to look at sort of a more general way of expressing the torque, because we did sort of two special cases. So I'm going to have a situation where the magnetic field is pointing to the right. And now we're going to imagine that my current loop is sort of at an angle, and if we look at it from the edge, on this end, the current's coming at us, and at this end, the current's going into the page. So you see what we're doing is we're looking at the loop from a side view. And we're going to say that the entire width of this is W, and of course, right the middle is where it's going to rotate about. If we do, the force is IL cross B. The magnitude of the force is ILB sine of theta, where theta is going to be the angle between the current and the magnetic field. Sorry. They're actually perpendicular to each other, so I don't need the theta there. Okay? So if I look at this end, remember this is the way the current's flowing, and I do I cross B, I'm going to get a force downward. And so that force, its magnitude is going to be IL. It's the length of the loop that is actually going into the page, so we don't see that on this picture. And then B. And then on the other end, when I do IL cross B, I get a force up. Now, when I want to find the torque, remember it's R cross F. Now, our radius vector for each piece is going to be the distance from here to here, which is W over 2. So I have W over 2. And then our force is equal to ILB. And then the angle between these two, we're going to call theta, and that's the sine of theta. But I have two of those forces, remember, one on the right-hand side and one on the left-hand side. They're both the same strength. And so I get W times L, I, B, sine of theta. This is the area, so it's I, A, B, sine of theta, which does correspond to, remember, this is equal to mu B sine of theta, which has the form of the magnitude you would expect if torque was equal to mu cross B. Okay? Again, remember that in this picture here, the mu would have the direction of the right-hand rule, following my fingers around the way the current's flowing, and perpendicular to the area itself, the surface area. So this would be the direction of my mu, just for kicks. All right, so hopefully that helps just kind of get you started on that last part of the chapter. Tomorrow we'll start chapter 28. Oops.